My name is Sylvia Tran, and I'm one of the organizing chairs for PyData LA. I'd like to welcome all of you to our second keynote for our conference. To the stage, we'll be welcoming Anima Anandkumar. She's a Bren Professor at Computing and Mathematical Sciences Department at Caltech, also a Director of Research and Machine Learning at NVIDIA. Anima's research interests span theory and practice of large-scale machine learning. In particular, she's been spearheading the development and analysis of tensor algorithms for machine learning. She's a recipient of several awards, such as the Bren Endowed Chair Professorship at Caltech, Alfred P. Sloan Fellowship, Microsoft Faculty Fellowship, Google Research Award, ARO, and AFOSR Young Investigator Awards, NSF Career Award, and several Best Paper Awards. She received her BTech in Electrical Engineering from IIT Madras in 2004 and her PhD from Cornell in 2009. She was a postdoctoral researcher at MIT from 2009 to 2010, an assistant professor at UC Irvine between 2010 and 16, a visiting researcher at Microsoft Research New England in 2012 and 14, and a principal scientist at Amazon Web Services between 2016 and 2018. So if you can please join me in welcoming Anima Anandkumar to lead us through our keynote on Tensorly, a flexible Python framework for machine learning, that would be great.
Thanks a lot. Thank you, Sylvia, for the introduction, and it's a pleasure to be here, and I'm very happy to see the community efforts here in LA, and PyData is really leading the forefront there. Anybody who hasn't heard of Tensor? I know maybe that's not the right way to frame it, right? So, it's there in the news a lot. There is TensorFlow, there's Tensor Cores, right? So you think every operation in AI is a tensor operation because of this terminology. But what I want to distinguish is the standard linear algebra matrix operations from tensor algebraic operations, which really expand into more dimensions. Like if you think of a matrix multiplication, you can multiply a matrix on either the left or the right, right? So that's the only two options. But now if you think of a three-dimensional tensor, you can multiply it in three of the directions. So it's expanding on the notion of matrix product to higher dimension. And similarly, if you think of decomposing a matrix, singular value decomposition is an algorithm we all study in engineering classes. How can I expand this to a notion of tensor, right? So can I think of a tensor as sum of rank 1 components? Or can I think of this tensor as a contraction over a lower dimensional tensor, which in the matrix case would mean you're multiplying, you're expressing this matrix as a product of two matrices, and then the dimension lowers, right? That's the notion of a low-rank matrix. In the case of the tensor, these two notions are actually different. When you express the tensor as sum of rank 1 components, that's a different notion from when you think of it as a contraction of a lower dimensional tensor into this higher dimensional space. The matrix is a special case of a tensor because it's a second-order tensor. But when we expand to higher orders, we get a richer algebraic set of operations. So we can contract in different directions. We can decompose in different ways. And in fact, you can think of different notions of tensor representations. You can go to hierarchical tensor representations that, in a way, could be also thought of as how you think of deep neural networks, right? You can, in the algebraic sense, you can relate the both in that way. And so that's where I want to use this talk to distinguish the standard use of tensors when we say TensorFlow or Tensor Core, which is to mean there's an array of numbers, some data that's represented as a multidimensional array, but we are still doing matrix and linear algebra operation. That's the standard usage, whereas I'm asking, can we take multidimensional data and truly do multidimensional computations on it? And that's what Tensorly as a toolbox enables you to do that. And it connects to NumPy, so you can do with standard linear algebra tools and expand on that to tensor algebra. Or you can also have PyTorch, TensorFlow, and MXNet. So you can define it as new layers in your neural network and now explore a new family of architectures through this framework. And in the meanwhile, if you have questions for me, I mean, about anything else too, like about general machine learning, I'm happy to take them while we get this set up. I think want to make use of this time to the fullest extent. Yeah. Yeah, so DMRG and all these algorithms are from the quantum simulations community for tensor networks, and they're tools like iTensor. So currently, they're not integrated, but this is what I'm talking to people in that community, like Garner Chan at Caltech. Our goal is to bring that together, but currently, that hasn't happened yet. It's a good question.
Are there any examples of Tensorly used with Redshift in AWS?
So, Redshift is a managed database, right? So to me, those are all the way you can bring in data. And then after that, what is the actual algorithm or neural network model that you use? That's where Tensorly comes in. So you can put Tensorly into SageMaker or a Dockerized framework and then run it. So the question is whether you can go from Redshift to SageMaker. I think that was on the roadmap. I'm not sure if it's already there now. Yeah.
So with your work at NVIDIA as well, is there specific hardware optimizations you're looking at to deal with actual tensor and multidimensional operations?
Yeah, no, that's a great question. A few years ago, I had a paper with NVIDIA researcher Chris Secca on asking what are the new higher order BLAS primitives, right? So if you think of BLAS level 1, so BLAS is basic linear algebra subroutine, right? So that's both for GPU and CPU, the very basis of vector and matrix operations. So to complete that thought, so BLAS1 is vector-vector operation, BLAS2 is matrix-vector, BLAS3 is matrix-matrix. And now if you go to a tensor, it's a higher order BLAS. And so there, what we asked was, can we utilize the current primitives like batched matrix multiplication to do more efficient tensor contraction? Like, with a tensor, again, you would have transpose operations just as in a matrix. You don't want to create new copies. That's too expensive. And so we started there, and now there is a big effort to ask different families of tensor contractions, how do we speed them up in CUDA? Can we create there's a new framework to speed that up and do it in place? Yeah, so I think I already gave you the motivation for a tensor, but maybe this is a better one with docs, right? For me, everything in life, docs make it better. So, the idea is if you're going up in the dimension, so the scalar is zero-dimensional object, it's just a point. A vector is one-dimensional, so it's a direction and the length of the line, right? So that's a vector. And now in two-dimension, you can think of it as rows and columns, but you can also think of it as a linear operator. It's operating on a space. And if you want to now expand it to more dimensions, similarly now it's, you have multiple dimensions. Each dimension is called a mode. So row would be a mode, column would be the other mode. So then you have the third mode, which is the third dimension. But again, you can think of it as an operator sense, as a multilinear operator. So it extends the notion of linear operator to more dimensions. But that's the technical usage. But what does that translate when it comes to the set of operations we can do? right? And that's what I'm interested in. And what it is applicable for. Yes, so why tensors are now very relevant to machine learning is we have multidimensional data. So if you think of the image, a color image, you have 3 dimensions because you have the width and the height and the number of channels. So if it's RGB, then it's 3 channels. But when you go through the layers of a neural network, you are also processing this in different ways, and that's why the term TensorFlow, right? Because you have the input as a tensor, and you have the flow of the tensor throughout the network as the output. So that's a starting example, and now if you go to video, you also add one more dimension, which is the time. And now if you go to multimodal data, so if you have both text and image as your input, your dimensions then expand. For instance, a visual question answering is a task where you are both given the image and the question as the input. And if you have to model text, right, the number of dimensions is the number of words in the vocabulary if you're modeling it at the word level. And so you need to kind of think about all these dimensions in data. And so tensors are most relevant especially for multimodal data, because you have lots of different dimensions coming together. So the question is, we have all these dimensions in data, how do we process them more naturally, right? And that's why we need to think of tensor algebraic operations. Let me just use this. Even then, it's not moving. Maybe you can help me just move the... Yeah, so the idea is, what is the processing of data that can lead to tensors, right? So even if my data is just vector data, you can think about the correlations in data, and that's a higher dimensional object. So typically, we think of pairwise correlations or covariances, right? So if X is a vector, you're looking at every pair of variables and looking at how correlated they are. And that gives you the standard correlation matrix. And if you're subtracting the mean, that's the covariance. So this is standard, but if you want to go to more dimensions, we need the notion of tensor. And so if you're now looking at third-order correlations, you now want to ask, between every triplet of my coordinates, I want to ask what's the correlation. And so this is operationally, it'll be now a cube. Right, so these are the correlations I want to manipulate with. So intuitively, pairwise correlations are the simplest. A lot of classical machine learning only operates on pairwise data. So if you know principal component analysis, which is to find the low-dimensional subspace where the data lives, that's only looking at covariance, right? So if you're looking at Gaussian approximation, that's only pairwise data. But as we start to have richer data and richer models, we are looking at higher order correlations. And the neural network implicitly is doing that because it's having all these nonlinearities. But we can also think of this explicitly expressed to the notion of tensors, right? So it can explicitly incorporate higher order correlations in the data. And so that's the other use of tensors. And so now that we have the use of tensors to represent directly the data or the correlations in data, the next question is, what kind of operations do we do on this? Right? So that's where we have the natural extensions of the matrix product to more dimensions, where now you're operating on each mode or each direction of the tensor. Right? So you have like possibly different vectors or even matrices or higher order objects operating on the tensor. So in this case, you're multiplying the matrix with this column vector. That means you're taking linear combination of the columns of this matrix. And now if you're multiplying this third order tensor along 2 of the directions, here you see it's a multilinear combination, right? And that's why it's kind of extending the notion of a linear operation to a multilinear operation. So it's linear in both the red and the blue colors. And so this is a natural extension. And so now you can see, you can directly think about what kind of weights should I learn across the different modes of the tensor. And you could get a nice dimensionality reduction by operating on it. And you would lose the structure if you convert it into a matrix. So you can always take this third-order tensor, flatten it. So flattening means literally that, right? Like you can just arrange the matrix slice one by one into a big matrix and operate on this. But doing so means you're destroying the structure. You're not using the fact that there's this third direction that makes it a tensor. And so that's the benefit. Like you can potentially keep all the information of the different dimensions and directly operate on that. And so now let's see how we can use these basic intuitions and create tensorized neural networks. So what is one of the standard neural networks, right? So for computer vision, what we have are these convolutional layers. So you take the image, you learn filters, and you pass them through these different layers, and you have some spatial pooling and nonlinearities. So this part is standard. And then when it comes to the fully connected layer, what we do in practice is to just vectorize this. So the output of a convolutional layer is three-dimensional because it has the width and the height and the number of channels which are due to the layers of convolution. But when you come to the fully connected layer, you're vectorizing it. You're converting this three-dimensional object into a one-dimensional object. And then you're learning what is the appropriate set of weights to multiply it with and do some nonlinearity. And then in the end, you have this vector that says what is my level of confidence of what category this image is about. Right? So that's the operation we have in a standard network. But how can we go beyond? So the main thing is here we are destroying all this three-dimensional information and directly just processing it as a one-dimensional object. And can we do it as a three-dimensional operation? And that's where we propose this tensorized network where we take the three-dimensional object and learn the contraction weights directly on the three dimensions. So you see now that these weights are more suited to the dimensions of the data, right? And then in the last layer, we call it a tensor regression because we are making this low-rank tensor, the set of weights, we can reduce the rank of the tensor and hence reduce the number of parameters. So the idea here is, if we did all this as a matrix, we wouldn't keep all the information that's present in all the three dimensions in this example. And so what's the benefit of this? The benefit is you can have much smaller networks. You can reduce the number of parameters in your network and still retain the accuracy. So as much as 65% you can save, right? You can save in terms of the number of parameters. And so this can potentially lead to better storage. You have more compact networks. It can lead to speed up because you're operating on a smaller network and still not lose accuracy. So this is a simple example of how by thinking about what are the different dimensions in my data and how does it change as I process it through the layers of my deep neural network, and how can I try to preserve that information and hence have a more compact network, we can best utilize the tensor algebra. So let me show some other examples there, if I manage to move to the next slide. And so before that, I guess, can you move one back? Oh yeah, here. So the Tensorly is a framework that make this possible, right? So the experiment I showed about the deep tensorized networks, we ran it with Tensorly, and Jean Kosaifi is the creator of Tensorly, and I worked with him last summer to further think about tensorized algorithms. And the idea is this is a Keras-like framework. So meaning that is a simple front-end API to define tensor operations in Python, and then multiple backends that you can utilize. So if you want to do scientific operations or basic linear algebra operations, you can use NumPy and SciPy. If you want to do deep learning, you have all the favorite frameworks here, but in the front end, it'll all look the same, right? So there's a set of basic operations that I'll show you, and then on top of it, we build tensor algorithms. So what I showed was for tensor with deep networks, we can define those layers. And we can also define the tensor regression, which is what we did in the last layer of the network. And the decomposition is the other framework where we decompose the tensor in terms of low-rank components. And so all this is available within Tensorly. So I'll also show you some of the other notebooks if I have time later. But as an example here with the PyTorch backend, as you can see, you just set the backend right in the beginning. And in this example here, we wanted to say the tensor is a low-rank Tucker tensor. I mean, that's a special kind of low-rank tensor. And you can just define what is the rank you desire in this tensor. And once you define this, you can attach the gradients, and you just set the optimizer as in the standard neural network training, and you can run the whole loss optimization. And so in a sense, it nicely plugs into the existing deep learning frameworks, and it's very lightweight. You can easily bring in the new tensor operations and integrate it with your neural network training. And so that's an example of this. Yeah, so this comes to the earlier question now. Suppose, how do I actually get the benefit of a smaller network, right? And for that, you need the primitives, the tensor primitives to be defined. And so one of my earlier projects was asking how we can do that effectively. And there's still a lot of work in this direction to be done. I mean, there's a reason why linear algebra has been used extensively in deep learning, and that's because we have highly optimized toolboxes with linear algebra. And with tensor algebra, it's still under development, right? And that's also part of it is historic because tensor algebra is much more involved. And usually when people in numerical analysis think about it, they require very high levels of accuracy. They always require it to be the same answer, right? Which is very different from what we care about in deep learning. So tensors are NP-hard, like a lot of these problems are NP-hard. You can't solve them exactly. And so that's where I feel that the progress lagged because of the hardness. Whereas once we've adopted deep learning, NP-hardness is not the constraint, right? That's not a barrier to see how they can be effective in practice because we know even what we think as computationally hard problems in the worst case instance work pretty well in practice. And that's where I think tensors will also see more of adoption because it can nicely expand upon linear algebra operations and better exploit the multiple dimensions in data. So I'll quickly go through this because I know there is more things I want to cover. But the main idea is this. I mean, currently we stop at BLAST 3 when we think of either the CUDA libraries or the LEPAC, right, the standard libraries for linear algebra, because that's the matrix multiplication, and they're highly optimized to run well. But with a tensor, it's like a higher order BLAST because now you have this third order tensor, and let's say you want to multiply it with a matrix in one of the directions, right? So this is the actual operation, but the problem is, you can always convert it into a matrix operation, right? But you may need to kind of reorder the indices. And if you do the copy, that's expensive. You don't want to do that. And so we asked, can we think of a new primitive to do that well? right? And that's where that was the earlier work. And so this is just saying the same thing I mentioned, right? Like, if you want to turn this into just a matrix multiply operation, you have to reorder the indices. And depending on what regime you're operating in, that can be a significant time in your computation, and it also requires extra memory. So this is not optimal. And so this is where these are the details in the paper, but it turns out you can nicely use an existing primitive called the batched matrix multiplication and build on it as a special case and make further optimizations, which we call strided batch gem. And you can almost closely match the performance of a single matrix multiplication in many regimes. So this is the blue is the single matrix multiplication, and this black is the our primitive. And so the high-level take from this is if you go into optimize the tensor operations, there can be a lot of benefits. In fact, now in some things we are developing, we're seeing it can be much faster than even BLAS operations, CUDA BLAS operations, right? So you can get the benefit of speed up once we have the primitives in place. And that's where we need also developers to think at all levels of the stack, how do I expand the library? How do I expand the primitives for tensor computations? How do I think of new algorithms, new ways to move data for these tensor operations that can make it more efficient? And I think after that, we'll definitely see a lot of benefits by using the tensor operations. So now I want to give another examples of use of tensors in time series. And here tensors are a natural, have a natural use case because time series we know can have very high order correlation, right? Because we know how the past kind of affects the future could be through higher order correlations, and that's very hard to model. And so in practice, we use networks like recurrent neural networks or LSTMs or long short-term memory networks, but we don't really understand, right, like they don't always work, and if they work, while they're working well. And so kind of to try to go deeper into that setting, can I get the next slide? Yeah. So this is the recurrent neural network, right? In the standard recurrent neural network, what you're doing is you're propagating your state. So you have this input, and you're also an output. The output could be like, what is my next prediction or the forecast, or it could be something else, right? So this is our standard recurrent neural networks. And we can, here the problem is what you're doing is you're still doing a simple first order Markov transition. You're just going from current state to the next state, and you're doing usually a simple nonlinearity to go forward. So this may not capture all the higher order correlations in the time series. And so our question was, how can we improve upon this? And this was the idea. So we can take the hidden states, and we can think about some more higher order polynomial interactions. So you can look at the correlations between a window of hidden states. But the challenge is if you directly look at the correlation, this high order correlation, that's a high dimensional object, right? Your dimensions blow up. And that's kind of overall the intuition too. You don't want to look at high order tensors directly. It's too big an object. Right? So instead, can we implicitly manipulate them and look at low-rank approximations of that? And that's what we did in this work, where there's a notion called tensor train, which looks at forming a train of the tensor modes and finding a low-rank decomposition. And so there are effective algorithms to do this well. And you can still capture the essence of high-order correlations that are relevant for forecasting. So by building this into the recurrent neural network or into the LSTM cells, you kind of build in more of the inductive bias. Like high-order correlations are needed for better forecasting. Can we build that into the network that we are training? And that's what we did here. And we see, can you go to the next one? We see that under traffic data set, so this was the standard LSTM, the blue line, and the red is the tensorized LSTM, which use the tensor train as a way to capture the higher order correlations better in our data. And you see that the long-term forecasting is much better. So this is the error, the root mean square error. So you can see that for the LSTM, as you go predicting into the future, the error blows up quite badly. And this is much more controlled when you do the tensorized LSTM. Because higher order correlations are especially relevant when you're forecasting way into the future, right? That's when you have to worry about it more, and that's showing up. And same with the climate data set. Yeah, so as a third example, I want to show the multimodal data. So if you now have not just image or text, you have the combination, you want to ask how to combine the features of these two networks. Let's say you have some convolutional network and some LSTM to extract them, but you still need to combine the two to come up with the answer. So in the visual question answering example, you want to ask, you want to say what the answer is, you want to combine both these features. So you can think of now forming some, correlation between these two sets of features, right? You want to compute the correlation between them, either first order, second order, and so on. So again, as you keep going to higher order correlation, if you directly compute this, that's too big an object, right? Your dimensions blow up. But can you do different kinds of tensor low rank approximations and directly learn this network end to end to find what is the right way to combine these two features? Like what's the right pooling mechanism that can appropriately capture the correlation between the image and the text? And so these are some of the things we are exploring how to do this. There's a complicated architecture, but the main thing I want you to take out of this is we are directly thinking of three-dimensional tensors when it comes to image, and that needs to be pooled with a one-dimensional text feature. And what's the right pooling? If I think about correlation between the three-dimensional object and a one-dimensional object, how do I directly express this, right? And how do I directly capture the relevant information from the correlation to come up with the answer? And so that's where tensors can be very effective, because you can directly manipulate these multidimensional objects. So typically what people do in visual question and answering is they'll convert this three-dimensional object again into a one-dimensional object. And they usually concatenate the image and the text. And that may not capture all the relevant correlation between the image and text. And so you may have a hard time coming up with the answer. But now, by exploring these richer set of networks that can capture higher order correlations more effectively, but more importantly, do that in a low-dimensional way. Still keep the rank low so you don't have too many parameters in your network, so you can learn more effectively and not overfit to your training data. You can use these tensor methods to do that well. And so another another area that I explored with tensors was to ask, can I do topic modeling effectively? In fact, this was my first project with tensors. I mean, we kind of happened to chance upon tensors when we were thinking of solving this problem, and that was before the deep learning era, so it's kind of coming a full circle now. And so what is the problem with topic modeling? So you have a whole corpus of documents, and you want to ask, what is the content in these documents, right? What are the topics being discussed? And this is, in a way, even more challenging compared to the other problems I showed, because there's no label data. So this is unsupervised learning. All you have are these text documents. You don't have any examples saying, oh, in this document, these are the topics that are discussed. Right? And unsupervised learning is considered hard because maybe you don't even know what to look for. Right? Somehow the patterns in the data have to be teased out in a natural way, and that can be challenging. And so in this example, for instance, we know that like when we read, we know that the topics that just, by glancing through the document, you can see will be government, information technology, and politics, right? There are multiple topics in the document, and that also makes it challenging. Traditionally, when people think of categorizing an unlabeled data set, they think of clustering, right? Can I put my data points into different groups? But for document categorization, that is not the right thing, because typically you don't have one topic in a document, you have multiple topics. So all these clusters will overlap, so you can't do a clustering algorithm. And so the algorithm, or the model that we utilized is called the latent Dirichlet allocation. There's been extensive work on this, where it's a very simple model, but but that's also its power, right? So what it's saying is every document has some probability distribution over topics. Let's say this is like, in this example, I don't know, 50% about justice, 30% about education, and so on. And how you're drawing each word in the document is from this distribution. You're first drawing the top topic, and then drawing a word according to how the words are distributed in that particular topic. Right? I mean, obviously, English is not generated this way because it's not just random draws of each of the word given the topic, which is independent. So you don't have that, but what's the, can I go back here? So, but what's the benefit of this model, right? It's called the bag of words model, and so it's only looking at the frequencies of the words. So in a way, it's ignoring all the grammatical structure and the style and other nuances that are maybe not the most important things for detecting topics. So what's very important for detecting topics is how do words co-occur together. So if I can understand the co-occurrence of words, maybe that'll really help me detect topics well. And in fact, even today, only this model or these class of models are used for detecting topics in long documents. Because if you go to those deep learning kind of frameworks, they only work on very short, like sentence level ones, right? And it's much harder to do longer ones. And so that's the benefit of the simple model, because it's asking, let me look at frequencies of words in documents, and can I learn the relationship of which words tend to co-occur together? And based on that, can I infer what the topics are? And so with that intuition, we said, how do I learn that model, right? Because what I want to learn is this, how are topics related to words? For instance, under topic education, what can I expect my distribution of words to be, right? Under a different topic, maybe that distribution of word changes. And as different words co-occur, can I detect that? And the idea is to look at triplets of words, how they co-occur together, and then to decompose that tensor. Because what is the intuition? I mean, if a word apple, let's say, occurs in a document, it's probably a fruit or the software company, right? Or the hardware and software company, right? So that's but you don't know just by looking at the word apple. Then you say word apple and orange together, maybe more likely it's to be fruit. But then again, there's another company called Orange too. So if you go to more such correlations, if you go to now apple, orange, and banana, then yes, most likely this is talking about fruit. But you can't go and manually look at all these such correlations and label these documents, right? So instead, this is automatically done at scale. It's looking at all the triplets, like triplets of words, and asking what are the dominant patterns that are coming out. So if they're prominently co-occurring together, maybe that's a topic that's coming out from those co-occurrences. And that's what the tensor decomposition does. It's teasing out the topics in an unsupervised way, even when you don't have labels of what the topics are. And that was the idea behind that. And that's expanding on the idea of singular value decomposition. So if you've done like SVD, you decompose the matrix into low rank components, and now you can expand the same to do with a tensor as well. And there's a lot of algorithmic nuances of how to do this at scale, how, if I have this very large tensor, I'm not going to form this, right? Because all I have is a vector of frequencies for each document. That is, how frequently do different words occur in each document. I don't want to form that into a three-dimensional object, because that'll be huge. So I shouldn't directly form that object, but I should implicitly manipulate that and get to the topics directly. So there's a lot of interesting algorithmic work to make that happen at scale. And this is something we worked on, and and we showed that this is possible. So there are also lots of advantages of doing this tensor method as opposed to other methods for topic modeling. I won't go into the details, but there's a lot of nice theory. You can show that this is guaranteed to converge to globally optimal solution under many natural conditions that we expect to hold in practice. And so this was available on AWS SageMaker. So SageMaker is a set of Dockerized algorithms that are designed for high performance. And while I was there, I helped the team build this tensor algorithm into LDA. And we see that it's much faster compared to open source frameworks like Mallet for topic modeling. So you get the benefit of faster algorithm and also similar or even better topic coherence, which is a way to measure how good is your topic model. And so you can see the benefits of doing tensor algebra at scale, that you will, you can come up with good benefits in the end. So in the last few minutes, I want to talk about some of the other efforts that are happening at Caltech, that can make use of the tensors, but also other areas of machine learning and control. So we have this drone testing facility where you kind of, this is a unique wind testing facility. You can see ultimately there'll be these are programmable fans. So there are about 1,300 fans there. And yeah, I think the video is slow. So ultimately there should be wind blowing out of those fans. So the idea is we can precisely control, no, I think I cut the wrong part of the video, but anyways, sorry. So that was kind of, showing different wind conditions and all this we can model well. And so this was supposed to play together, but somehow that didn't get into the screen either. I think it's pretty dark here. You don't see that very well. But on the left here is the standard PID controller without learning, and it was just hovering around, whereas the one where we did the learning landed well. But I don't think you can see very well in the screen. And you can see, again, it's hovering because it takes a lot of time. And here I wanted to kind of say, there's so many things we cannot model well in practice, right? Because, and the ground effect is one of them. When the drone is near the ground, it's too many aerodynamics forces that are hard to model. And whereas we can learn from data and then improve this. And so there's a lot of rich possibilities of taking learning algorithms to drones and robotics and other control systems. And I see tensors playing a big part there with time series and other multidimensional sensors. Yeah, so to conclude, tensors are higher dimensional extensions of matrices, and we can expand the set of operations we do with matrices to more dimensions. Tensor contractions are at the core of it. And we can do operations like tensor decompositions, tensor regressions. And this will expand the class of neural networks we can use and better capture the dimensionalities in data, as well as higher order correlations in a low rank form that makes it feasible to generalize better and also have more compact networks. Thank you.